Hello, welcome. In this session, we're going to review thermoforming core for weight and material saving using adaptive mold technology. First, I want to introduce myself. My name is Gulnur. I am R&D manager in Metyx Composites, which is a global company located in United States and Europe also. So I am specialist on polymer science and technology. I've been working over 15 years in the composite industry, focusing on the technical textile, manufacturing engineering, and characterization of polymeric composites. For the core study, we will be using wind blade spoiler mold. So a spoiler is a part on the wind blades. It's a secondary component, which is meant to easy transportation damage while enlarging the swept area of the blade to increase the efficiency of the rotor blade. So the core being reviewed is PET. It has a 135 kg per meter cube in 30 millimeter thickness. Which one is no cut on 0, 90 direction, no grooves on it. So we use adaptive mold technology to form it. The other one for the comparison is again the same material. It has cuts on it on the 0 and 90 directions for the core panel using traditional layup. So composite parts we use in this trial is a development in accordance with the OEM lamination plan is used for both core solutions under review. When we're using adaptive mold technology, we are going to use these 3D CAD files. So we took 3D scans of the parts, namely high pressure and low pressure. Actually, the spoiler has two sides, high pressure and low pressure. We manufacture both, but in this session, I just present the high pressure side because we have limited time. So we took 3D scans of the parts and we converted them from the STL files to CAD files. So the mold we used developed in 3.6 meter long. So PET core form with adaptive tool is 30 millimeter thickness. For the comparison, we use grooved countable PET is used again. It has grooves on it, positions near the 30 millimeter center line, and it has a 1.2 millimeter wide width. So main focuses are the resin quantity, which we try to see if we have any resin weight reducing consumption, and also dimensional accuracy, the core thermoformed across the mold versus time, and weight savings associated with that. So just have a quick look at the adaptive mold components. So here, this machine allows the molding components that shape the surface to be used for formwork. It has a protective sheet on the top, and it is a membrane with a silicone membrane, and it has supporting magnets and flexible rod system also. So steering components are for accurate 3D positioning of the mold surface. 3D laser, control units, linear actuators, and electrical stepper motors here. Formwork add-ons for easy and repetitive unique shaping of the panel site is possible. Here, laser-guided positioning is the key. So on 3D top, we can lay down all material, whatever. It can be laminate, it can be fabric, also it can be core material. It doesn't really matter what the substrate you use. Laser is going to help place those components very accurate positioning. Let's look at the business case revolving around adaptive mold technology by comparing with the traditional panel manufacturing method. In traditional method, you will need a lot of labor hours, a lot of materials associated with the developing that shape just only one time. In adaptive mold, allows you to do the same thing, except you do it very quickly, and it's a 3D file that you can upload into the machine in the computer-aided manufacturing. and develop a shape that you need 3D drawing. Basically, you are there with a matter of managing, you can form that adaptive mold, whatever shape you need. And then go ahead with your laminate, demold it, and bring that mold back down to the first station, less than 5 minutes if you want. So just in time delivery is also a great opportunity for this. Adaptive mold we use in this trial has overall dimensions 2.6 meter and 1.6 meter. Actually, the usable area is 2.4, 1.4, which is certainly enough room for this trial. For the forming core of spoiler parts, we need to understand how the core's performance is going to work under the heat. What is the behavior of that? So to do that, we measure external temperature core measurements using traditional oven. We ramp up together, core and the oven, ramp up to 165 degrees C. And then we let the foam sitting in the oven at that temperature 5 minutes. And then pull it out after 5 minutes and measure the surface temperature in 90 minutes to see temperature changing on the surface. In order to understand how much time we need to form the foam, when we taking from the oven, put it into the back to the mold to form it, what is the retaining time to shape it? Here on the graphic, you see almost 50% drop down in the temperature in 5 minutes. So the graph shows that if you want to maintain for forming core, we have about 5 minutes to do that, to get from the oven, put it under the bag, and pull to the vacuum is about 5 minutes before it starts to lose its thermoforming properties. Not only external temperature, we need to monitor internal temperature also. To do that, we drill the 100 millimeter hole into the center of the core, and then we place a thermocouple to measure temperature. We apply the same basic temperature conditions as we did in external temperature trials. For the forming of cores, spoiler trials, we need to understand how the core's performance is going to work under the heat. So here you can see the internal temperature drop down, is less than 20 degrees C in 5 minutes. So we have a little bit more time when you compare the external. So we have time 10 minutes. So this is our time we associated with actually forming this core. We are from 0 to about 10 minutes cycle time before it starts to lose forming properties again. So we compared the two temperature changes here. If we look at the differences, it started with high differences in the first 10 minutes. Looking at the result, we can say that, again, 0 to 10 minutes, we have enough time for this course in a secure way. It's going to be retain its shape. So other measurements was on the spring back. Spring back, what we call is the memory of the foam, what it wants to turn back its initial straight position. Basically, we revive the foam after the cooling apart the back. And after we remove the vacuum bag, we measure the distance between the mold surface and the edge of the core on the 4 points. If we look at the result, we see that the spring bag after reaching temperature, after the 1 minute was not too much. It changed between the 3 millimeter and 6 millimeter here. 0.6 is 6 millimeter, a little bit more aggressive than 1 and 2. So basically, after 1 minute, you see pretty acceptable because we can pull that back down with the vacuum back. We can make the fabric align with the material, with core, even it's 6 millimeter. So we can bring back that to its original shapes around the mold with a little problem. So certainly, after the 120, 630 minutes, it gets a little bit crazy, but you can see pretty much stable out after about the 360 minutes, so you don't have too much spring magnet. It's retaining its memory. To get the required shape, calibrating adaptive tool is needed. This tool has a unique software program, so you can simulate. Also, you can see, develop your shape, and you can see how it can be positioned on the mold also. Its name is Rhinoceros 3D Rhino 6 simulation program. So let's get back to the trials again. This is the core we use to shape in adaptive mold, which has no cut on it, no groove or no drill. So forming the core on adaptive mold, we use, as we mentioned in the beginning, PET, 30 millimeter thickness. Core is heated for 10 minutes at 110 degrees C. And then after that, we place it under the vacuum for 20 minutes on the mold. So we use OEM traditional laminate sequence plan here. 2 layers of 3-axial glass fiber, 1 layer biaxial belong PET, and then again 2 layers of 3-axial and 1 biaxial across the mold. Here you can see first step during our trials, biaxial, and the second steps, 2 layers of 3-axial. So you can see on the top 4 pictures, we lay down the thermoformed core. There's no putting into forming a shape. We don't use any force, and lay down quite nicely on the tool surface. We just here use the classical laminate infusion preparation. We applied vacuum tape, pill ply, perforated release film, and flow mesh after that. And then it's a classical lamination with the epoxy infusion system. So we applied the 15 minutes drop test. All things is identical with the classical infusion, exception of the PET core being thermoformed with the adaptive mold here. So this is the untrimmed, demolded parts produced with the thermoformed core. So the other comparing core has the cuts on 0 direction. It has the grooves. So you can see the same laminate sequence in biaxial and triaxial fiber lay down. And then on the top 3 weaves, you can see the PET core. It has lots of the grooves and the cut on it. We did not experience in our thermoformed PET. Again, same infusion preparation, classical epoxy infusion. So, core processing results. Basically, in the standard core, you can see on the left side, fabric has the weight as a 22 kg, resin 29, and PET core is 11.8. So with the adaptive mold, we get the fabric is close to the counter, it's at 23 kg. Resin is 19, which is very low. So we have a great reduced resin consumption here. PET is the same. So the infusion, empty infusion conditions are identical. Here the 80 minutes for standard core and 122 minutes for the adaptive mold. This is the infusion time. Actually, there is no movement we made to reduce the infusion time on the, or increase the processing time. We just focusing on the resin consumption and weight savings, building cost material to reduce the cost. So, there is obviously balancing acting to understand resin weight, part weight versus process time. It's But now we did not concentrate it. But if you look at the part weight here, for the standard core is 63.5 kg, and for the adaptive mold for thermoformed core is 53 kg, which is very low. It's an enormous, tremendous part saving. Thermoform core was able to reduce the resin consumption 35%, which is huge. Considering the resin prices in these days, this is really, we have to look at that. So part weight savings with the thermoform core is about 15%, so you are saving building material costs and the part weight associated with that. So we use this thermoformed core with the adaptive mold in the marine application too. This is another case. MAT is a particular boat builder. So we produce this with the same method, a sailboat. As long as the 12 meter, we use a wine elasto resin system. So we use the classical infusion process. 90% of all core panels were thermoformed. Not all pieces we had form, right? But some of the lengths were a little bit off form. Fitting core, fitting part to part had to be compromised as well. But despite that all, we're still saving of over 50% labor time, which is huge for the markets. This particular boat builder, MAT, produced 7 hulls using standard core, countable core materials. So hulls used a total of 270 kg resin with less than 1% variance. But using adaptive tooling thermoformed the whole core sheets, a weight savings on hull is around, we achieved 8%. And the resin consumption reduced of 20%. That was, we are looking for a sailboat. We are looking for the market. We have a short video here how we use adaptive mold and how we manufacture this hull with the thermoformed core. G4 has proven the ability to reduce component weight and part cost. The use of adaptive tooling allows the fabricator to reduce overall production cost compared to one of the tooling required for forming shapes, and reduce delivery time. Adaptive molds have the ability to be configured and reconfigured in less than 5 minutes, and reduce storage. Storing the mold or form shapes can be accomplished on a memory stick versus taking up the valuable floor space. At the end, you can get very valuable floor space and ground space too. Thank you very much for attending. So for the details, you can visit our booth. Also, if you have questions, I can answer right now.